The discussion will start after the next speaker, and the next speaker is Professor Dr. Martin Heimann. He is from the Max Planck Institute für Biogeochemie in Jena in Germany. The title of his talk is Freshwaters and Rivers, an underestimated link in the global and regional carbon cycle. He received his PhD in physics from the University of Bern. Then he went to the US, to the Scripps Institute of Oceanography in La Jolla, and then he went back to Germany again as a senior research scientist and was group leader at the Max Planck Institute for Meteorology in Hamburg. After that, he became a scientific member of the Max Planck Society and also director of the Max Planck Institute of Biogeochemistry. And he is now also an honorary professor at Friedrich Schiller University in Jena, Germany. Martin Heim.
Good morning. Thank you very much for the nice introduction, and thank the organizers for inviting me and giving me the job to talk about this topic. As you know, I am, and you saw from my biography, I am not an aquatic or limnology scientist, but I have been studying the global carbon cycle as an entity in the climate system, and I will therefore in my presentation give you a bit the view from outside, what we expect from the aquatic sciences to provide us the information in order to make better prediction of how the carbon cycle behaves in the Earth system. Eve has shown these kind of pictures, which demonstrate sort of the major flows in the global carbon cycle as compiled by the recent IPCC report. And he mentioned, that indeed these types of fluxes which are mentioned here are relatively small numbers compared to the gross exchange numbers, especially if you compare it like with the gross fluxes of GPP or the amount of carbon that's fixed by the vegetation, or also what is exchanged annually just simply by physical gas exchange with the oceans. These numbers are relatively small. Nevertheless, if you actually take this plot and sort of make the budgets, just add them up, and sort of look at the net fluxes between the reservoirs, then the situation becomes a bit different, and that's what's shown here. You see, if you look at the net flux between the atmosphere and the ocean at the moment, based on these estimates, it's only 0.6 petagrams carbon per year with the uncertainty of 0.4, and if you compare this with what's coming laterally in, this is not negligible. Of course, the different processes behind it, but nevertheless, at least quantitatively, it's not negligible. And the same on land. If you take the net budget of the uptake inferred with the net budget of the land from the atmosphere directly would be 1.4, and this is also comparable to the fluxes which are shown here, and Eve has addressed this point as well. So, in terms of magnitudes, these fluxes are really not negligible and have to be looked at. And especially this is going to be one of the main points of my talk, is if you want to assess the carbon cycle. In terms of measuring it, we usually measure these kind of fluxes, and there we have to really take the freshwater fluxes, or fluxes that go into freshwaters, have to take them into account. Eve also mentioned this volume, the scope 13. This is indeed also for me one of the first publications where really the freshwater carbon cycle was put into the whole carbon cycle discussion, and Stefan Kempe wrote a nice chapter there where he basically addressed the main questions which we still have. And here is sort of a picture. He looked at the different reservoirs. He did not indicate the actual masses in there, but he sort of looked at the PCO2, and the numbers here sort of are given negative 10 logarithm to the basis of 10 of the PC2. And if you're brave, you even can turn this into sort of carbon concentrations in the different reservoirs and potentially come up with sort of an early assessment of the carbon in the freshwater cycle. But he concludes, in this chapter that probably none of these fluxes will be larger than 10 to the power of 14. So that would be 100 teragram or 0.1 petagram carbon. Nevertheless, our attempt to investigate them shows how ignorant we are about the flow patterns and flux rates of carbon in connection with the freshwater cycle. And I must say, I'm not so sure, this 40 years ago, how much more we have progressed. Nevertheless, he puts this point here, 10 to the power of 14, 0.1 petagram. He meant sinks. This is not the flux per se, but sinks. And this is indeed the main thing, is even if the sink, I do not think that, carbon in freshwater systems will constitute a major sink for, excess carbon which we put into the atmosphere or into the system. But nevertheless, it's a pathway. And if you look at the pathway, then this number goes up, as Yves has already shown. So I have basically three sort of key points I want to convey in this talk. Carbon in freshwater bodies do not constitute large carbon pools. Hence, they can't constitute sources or sinks of global significance. That's accumulating carbon in freshwater pools. Carbon fluxes through freshwaters are comparable to other important carbon fluxes and need to be taken into account in carbon budget studies. And I will show a few of them just in the following. And then I think what Yves already mentioned also, that changes in freshwater carbon transport patterns by modifications, and I will come to that in the end, they might be relevant, certainly for regional assessments, in particular with mitigation activities. An old problem, which is in the carbon cycle been very prominent, in the 90s, was this existing of the northern hemisphere CO2 sink, which is sort of exemplified here. What is shown here are sort of measurements of the atmospheric CO2 concentration, seasonally corrected and sort of plotted versus the concentration measured at the South Pole. And everything is plotted here versus latitude. And the blue dots are sort of measurements from individual stations, and red dots are simulated concentrations using an atmospheric transport model, taking everything, movements of air into account, but just forced only with the fossil emissions, which of course take place mostly in the northern hemisphere. And you see this discrepancy between this fossil fuel simulation and the observations, which sort of indicates that there is a northern hemisphere sink at place. And of course everybody thought that this has to be inland, because after all the continents in the northern hemisphere are much larger. And so this has fostered a huge amount of studies over the last 2 decades, this finding which was sort of coming up at the end of the 80s. And the magnitude of this is sort of in the order almost of, imbalance between the hemisphere, about 2 petagrams. But already soon after this finding, it was hinted or suggested that possibly the river erosion fluxes, which are also hidden, of course, in this pattern which the atmosphere sees, might actually contribute. And I want to attract your attention to, once in this plot, this is how the northern hemisphere sink is portrayed still in the present IPCC report. You still see here sort of the fluxes estimated by various methods. Plot and blue are ocean, green is land fluxes, sort of plotted versus latitude in 3 latitude bands, northern hemisphere, tropics, and southern hemisphere. And you clearly see that if you add land and ocean together, which sort of gives up these purple colors, you see this sink in the northern hemisphere. So this sink in the northern hemisphere, extratropics, is a fact, is something we have to live. We want to explain it. I mentioned that possibly the erosion fluxes contribute this, and this has been demonstrated in a modeling study by Aumont and others which was published in 2001, where basically this flow of carbon in the system has been taken into account and modeled. To do this, you need, of course, a model of the weathering. You need to basically take into account regionally, how much carbon is by weathering taken out of the atmosphere, and you also have to take then the river routing in effect into account and put everything then back in the ocean. And then you, of course, need an ocean model, to deal with the carbon and figure out what happens if the carbon in different forms, as inorganic or organic carbon, how long does it take until it's be remineralized and so on. And then, of course, it will be distributed and sort of moved back. And the presumption here is that this is a steady-state system, but nevertheless it shows up in the atmospheric measurements. And this is sort of what they came up here, zonally plotted, zonally integrated. This is the flux from the south to the north, and they see that because of in the northern hemisphere, because of the erosion effects, the land actually takes up some carbon, which makes this a sink, and which then through the ocean is at least to some substantial amount outgassing in the Southern Ocean. This causes a slight imbalance between the different hemispheres, and in fact, if you put it into a model, this river effect already can account to about a third of the Northern Hemisphere sink. This is something we have to take into account. This is a modeling study. It's difficult to verify directly, but nevertheless, we have to take this into account. It illustrates the potential of these fluxes. Next is what we do now with the technique. I showed you the gradient before. Now, this is sort of the technique which now has become very popular in the carbon cycle community, to take atmospheric measurements, use atmospheric models of transport, and invert them for the surface fluxes which are maximum compatible with the observations. And here is sort of an example of such a picture. This is the total flux which the atmosphere sees, which is of course dominated by the fossil emissions in these areas. But then if you subtract the fossil emissions, you end up with this kind of background or natural source sink distribution, and which you then try to attribute to processes. And we have to realize, usually this is taken as a sort of, for instance, as an indication that higher latitudes here over land are clearly sinks for carbon. Ocean, there's places where it's outgassing, and other places where it's taken up. But you have to realize this is not necessarily the extra sink of CO2, which is induced by the increase in CO2 in the atmosphere, but this also includes these kind of erosion fluxes which are behind it, and they have to be taken into account, and they're not negligible. Now, regionally, it's been even more important. Regionally, when you look at this, and I just show you an example for CarboEurope. In Europe, we want to figure out what is the carbon budget of the continent, because there are two aspects of it. On one hand is the scientific aspect. What are the different ecosystems contributing to the uptake or release of carbon? But then there's also the political component in it that we would like to verify which country is actually emitting CO2 or storing CO2 to particular practices. So this is a big project, and that has developed a large observing systems, both with ecovariance measurements but also with atmospheric measurements. But then if you look at this and want to understand and compile and sort of try to bridge the top-down and the bottom-up method, you actually realize that you also have to look at the carbon fluxes through rivers. And here is sort of a compilation which has been made for this project. Basically, you have to estimate fluxes for this chain, because these fluxes which are in the atmosphere, they're not negligible. We're talking here about teragrams carbon per year. The total European budget, which is coming on the next slide, is on the order of 300 teragrams. So again, these fluxes, both from rivers outgassing, from estuaries, but then also the coastal oceans, which are sort of confounded, this is quite large. So in the net, it's only 30 if you add this up, but overall, it's not negligible. So here is sort of latest numbers which we get, and we break down and we see the different contributions from the different types of ecosystems. And we have to also include horizontal or lateral transport from trade to Europe. But then the freshwater riverine fluxes they're comparable with quite a few of these phases. So we have to monitor and take them into account, quantify them. Another example where also river fluxes are critical, has been the contribution to the Amazon forest sink mystery, which has been compiled by finding out that the Amazon River is actually outgassing substantial amounts of carbon. And it's sort of illustrated here, the puzzle which is arising is that if you measure the uptake of Amazon forests with ecovariance techniques, you find large sinks, the order of 300 teragrams carbon, if you scale it up, 300 teragrams carbon per year. Whereas if you go into the forest and measure their growth, it's only about 100 or maybe, and the soil can't be 100, this is estimated. So you find there's a mismatch between the two types of measurements, and clearly the realization that lateral transport to the river and the outgassing here has, and actually makes then a closed system, or sort of makes the measurements compatible, actually contributed substantially to our understanding of the carbon cycle in this area. Next, one of the most prominent topic which is in global carbon cycle research is the feedback problem. We know that we put the emissions of CO2 into the atmosphere and it's distributed in the system between ocean and land. We also manipulate land biosphere by changing land measurements. But then with CO2, increasing CO2, we also modify the climate, and this feeds back on both systems. And to quantify this is a very difficult task. There's a question, riverine systems or freshwater systems also play a role in this business. If we look at what is actually included in such models on the terrestrial side, and there I second Yves' comment, it's very simple at the moment. These are the sort of major feedbacks which are currently included in our models, in so-called Earth system models, meaning climate models which include a dynamic carbon cycle, in this case the terrestrial carbon cycle. So basically compute stocks, vegetation, and photosynthesis, and so they have these kind of feedbacks are included both on the CO2 concentration, which then also fertilizes the vegetation, but then also through temperature, which sort of has effects on growing season length or also on heterotrophic respiration. Well, that's all. That's all that is included in this type of models. And based on this, then the global simulations are performed. Like here, well, you must have seen these type of things, and where one tries to assess what will happen to the carbon cycle if the climate is coupled to it. And you see that usually the inclusion of the coupling feedbacks is positive, meaning that more with rising temperature, also more carbon will be released, so enforcing the whole global change. If you look at the individual results, you see that these are the present crop of models which show, how the land uptake will progress into the century, towards the end of the century. You see a large disparity of simulation responses, showing that we clearly have not yet done our homework. We really have to make these models more occur and validate them and test them and to make a coherent story. In the ocean, the situation is a bit more clear, but more coherent. But nevertheless, this is a major unknown in predictions of the climate system over the century, and for any of the scenario calculations which are needed for IPCC. This is the climate effect. I'll move on to the thing. Just summarize it here. We are talking about. This is sort of what the base simulation of the emissions which we put into the atmosphere. This is sort of the uptake by land and ocean, shown here in the green line. If you had no clear climate feedback, if you include the climate feedback, you reduce this. The magnitude is about 2 to 5 petagrams carbon per year flux. So this tells you already that, well, if you change the fresh river transport fluxes, significantly even, I do not think that they will matter on the global scale. These fluxes here are much larger, or the uncertainties also associated with them in modeling. So if you include them in the models, it's much better. However, and Yves has shown this already, if you look at sort of the land use effect, which is not included in the present coupled carbon cycle climate models, then we see this dramatic effect that if we go from, say, from a forested area to a crop-based area, we increase erosion fluxes, well, we increase uptake of CO2, which then, through the changed water cycle, also leads to this export of bicarbonate to the ocean. This is a major effect, and that has to be taken into account if we talk about sequestration practices, afforestation measures, which are highly discussed for many places of the world. Is this effect as large as it's shown in these first studies? This is something we do not know, and we have to improve our knowledge here. I mean, just to flag you the thing, you know, I mean, here in the Mississippi River, we clearly see a change, but in the Yangtze River, you know, it's not like that. So there's still an open question. This, I think, has to be monitored and documented for quite a few places of the world so that we can make reliable predictions. I come to my conclusions. I basically go back to my key points. You know, I think the carbon freshwater bodies are too small. I do not think that they really end up being important in terms of sort of ultimate sinks for excess CO2 of global significance. But the flows through them, they are comparable to others, and they need to be taken into account in budget studies. And these budget studies are increasingly being made and very critical. And so we need a better quantification because all those numbers are relatively uncertain. And we also need sort of a system in place which monitors them and compares them and continues to monitor them over a substantial time. On the feedback level, I think on a global scale, I do not think that climate feedbacks on the freshwater carbon cycle will have an appreciable large effect. But the transport patterns and changes in composition, is critical if we look at, say, mitigation options, and therefore has to be studied much more carefully than up to now. Thank you.
Thank you.